This is another example of fixed beam analysis using consistent deformation method. Let us consider a combination of loads. The question is given as analyze the fixed beam shown using consistent deformation method. Draw shear force diagram, bending moment diagram, and elastic curve. So there is a fixed beam on which there is a partial UDL of 30 kilonewton per meter over a span of 3 meters, and also there is a concentrated force of 40 kilonewtons, and the distances are as shown. So let us consider these points as A, B, C and D, and let us consider that EI is constant. So we are supposed to analyze this and draw the shear force diagram and bending moment diagram. So we know there are two consistent deformation equations that we can use. One is theta due to loads plus theta due to redundant is equal to 0, and theta is represented as area of BMD divided by EI. And the second consistent deformation equation is delta due to loads plus delta due to redundants is equal to total settlement of supports, and delta is written as area of BMD divided by EI multiplied by centroidal distance. So here we can split this entire fixed beam into simpler beams of cantilever. So one will be cantilever with partial UDL. This is 30 kilonewton per meter and 3 meters. And one more will be fixed beam with point load 40 kilonewtons. So this will be 3 plus 1.5, that is 4.5 meters, and the remaining is 1.5 meters. This point A, point B, and this is point D. And let us choose the redundants as reaction at B and moment at B. The direction of the redundants is your choice. It can be taken in any direction. And now the next beam will be cantilever with the redundant RB, and this span is 6 meters. And one more beam will be cantilever with moment MB, and this is 6 meters. So these are the simpler beams which we can divide into. Now we have to draw the BMD for each of these cantilever beams. So for cantilever with UDL, we know it will be a hogging BMD with parabolic variation. So the BMD is like this, and this will be hogging, and the moment here will be 30 into 3 into 3 by 2, which is 135 kilonewton meter. And these are the points. This is 3 meters, this is 3 meters. And for cantilever with point load, we again get a hogging BMD with triangular variation. So, and the moment here will be 40 into 4.5, that is 180 kilonewton meter. This is 4.5 meters and 1.5 meters. And cantilever with RB, we get a sagging BMD with triangular variation, and the moment here will be 6 times RB, and this is 6 meters. This will be sagging. And for cantilever with moment MB, it causes a hogging BMD with triangular variation. So this will be MB, which is hogging. So these are the bending moment diagrams for each of these cantilever beams. And we have to consider the centroidal distance from the centroid till the redundants for each of these BMDs. So these are the centroidal distances. Now we can apply our consistent deformation equations to each of these BMDs. So for the first BMD, if I'm applying the first consistent deformation, that is theta is equal to area of BMD divided by EI. For the first BMD, it will be minus 1/3 base into height divided by EI. And for the second BMD, it will be minus half into base into height divided by EI. And for the third BMD, it will be plus half into base into height divided by EI. And for the fourth BMD, it is rectangle, so it is minus 6 into MB divided by EI. This is equated to 0. We can take 1 by EI as a common factor and send it to the right hand side, which gets cancelled. And we can simplify these values as minus 135 minus 405 plus RB into 18 minus MB into 6 is equal to 0. Or we can write this equation as 18 RB minus 6 MB is equal to 540. So I'm keeping RB and MB on one side and sending the constant terms to the other side. So I get this equation, and let us consider this equation as equation 1. So this is by applying the first consistent deformation equation. Now let us apply second consistent deformation equation by considering delta which is given by area of BMD divided by EI into X bar. So for the same terms, we have to multiply with the centroidal distances X bar. So for the first BMD, it is given as minus 1/3 into base is 3 meters, height is 135 divided by EI multiplied by the centroidal distance will be 3/4 of 3 plus 3. So this will be 3/4 of 3 plus 3. For second BMD, it is minus half into base into height. That is the area. That is half into 4.5 into height is 180 divided by EI, and the centroidal distance will be 2/3 of 4.5 plus 1.5. That is 2/3 of 4.5 plus 1.5. Then the third BMD is sagging. So area of BMD is half into base into height, and the central distance is 2/3 of base. So this will be half into base into height divided by EI multiplied by 2/3 of base. And the last BMD is rectangle. So area is 6 into MB and central distance is half of 6. So this will be 6 into MB divided by EI multiplied by half of 6. This is equal to 0 because there are no settlements of any of the supports. Now we can take EI as a common factor and send it to the right hand side, which gets cancelled with 0. Now upon simplification, we are left with minus 708.75 minus 1822.5 plus 72 RB minus 18 MB equal to 0, and this can be further written as 72 RB minus 18 MB is equal to 2531.25. So this is our second equation. Now here we have two unknowns, RB and MB, and here in equation 1 we have two unknowns, RB and MB. So we can solve equation 1 and 2 to determine the values of the redundants. So we find RB as 50.63 kilonewtons because it is a reaction. The unit will be kilonewtons, and MB is 61.88 kilonewton meter because it is a moment. The unit will be kilonewton meter. So these are the two redundants. Now once we know the redundants, we can calculate support reactions. So this is our fixed beam on which there is a partial UDL and there is a point load. The UDL is 30 kilonewton per meter over a span of 3 meters, and the point load is 40 kilonewtons and the distance is 1.5 meters. 1.5 meters. This is A, B, C, and D. So now we have determined reaction RB as 50.63 kilonewtons, and this moment is 61.88 kilonewton meter. Right now we can also calculate the reaction at A. So let us say this is RA. Now we can apply the equilibrium equation. Sum of all vertical forces is equal to 0. So we get RA plus 50.63 is equal to 30 into 3 plus 40. That is, I'm equating upward vertical forces to downward vertical forces. And from this equation, we can calculate RA, which is found to be 79.37 kilonewton. Right? So RA is 79.37 kilonewton. So now we know all the reactions. So we can draw the shear force diagram in kilonewtons. So this is our reference. So at this point A, there is an upward force of 79.37. So it will be plus 79.37. From point A to C, there is a UDL acting downwards. So we have to subtract it. So 79.37 minus 30 into 3, it will be minus 10.63. So it is an inclined variation to 10.63. From point C to D, there is no force, so it will be constant. At point D, there is 40 kilonewton acting downward, so we have to subtract it. So it will be minus 10.63 minus 40, so that will be minus 50.63. From point D to B, there is no force, so it will be constant. And at point B, there is an upward vertical force of 50.63. So here we have to add it. So minus 50.63 plus 50.63 will give us 0. So this is point A, this is point C, this is point D, and this is point B. So above the reference is positive and below the reference will be negative. This is our shear force diagram. Now we know that maximum positive bending moment should occur somewhere in the UDL region. So we know here at this point the shear force is 0. That is where the bending moment will be maximum. So let us locate this point. Let us consider this distance as x. So this distance will be 3 minus x. So using these two similar triangles, I can say 79.37 divided by x is equal to 10.63 divided by 3 minus x. So the value of x can be determined, which will be 2.65 meters. Okay, so what it means is at a distance of 2.65 meters from A, we will get the maximum bending moment. So somewhere here, let us take a section as 1, 1, and at this distance of 2.65 meters, we will get the maximum bending moment. Now to draw the bending moment diagram, we have to calculate bending moments at various points, and the sign convention used is sagging bending moments are positive. So we know at point B we have a hogging moment. So moment at B is hogging 61.88 kilonewton meter. At point D, moment at D, if I consider right hand side, will be, yeah, so this is hogging 61.88 and 50 into 50.63 into 1.5, this will be sagging, so it is plus 50.63 into 1.5. So this is calculated as 14.07 kilonewton meter. And moment at C, if we consider right hand side, will be hogging 61.88 and 50.63 into 3 meters, which will be sagging. So that is 50.63 into 3 sagging, and 40 into 1.5, which is hogging. So it is minus 40 into 1.5. So this will be 30.01 kilonewton meter. And moment at A, if we consider right hand side, will be at this point. So it will be 61.88, which is hogging, and 50.63 into 6 meters, which is sagging. So 50.63 into 6, 40 into 4.5, this will be hogging. So minus 40 into 4.5, and due to UDL it will be 30 into 3 into half of 3, which will be hogging. So it is minus 30 into 3 into 3 by 2. This is calculated as minus 73.1 kilonewton meter. These are the moments at various points. Now we also have to calculate the maximum moment at section 1, which is at 2.65 meters from point A. So that can be calculated as, so here moment at section 1, if I consider say left hand side, yeah, so here if we consider left hand side, we have moment at A, which is minus 73.1, so that has to be marked first. So here at A I have a hogging moment, which is 73.1. So now at this section I have a hogging moment due to MA, and I have a sagging moment 79.37 into 2.65, and hogging moment 30 into 2.65 into 2.65 by 2. So this will be minus 73.1 plus, due to the reaction it is 79.37 into 2.65, that is 79.37 into 2.65, and due to UDL it will be hogging, that is minus 30 into 2.65 into 2.65 by 2, right? So this is calculated as 31.89 kilonewton meter. So this is the maximum positive moment. Now we know moments at various points, so we can draw the bending moment diagram in kilonewton meters. So this is our reference. This is point A, point B, point C, this is point D, and somewhere here we have 2.65 meters from A. So moment at A is minus 73.1, and moment at B is minus 61.88. Moment at C is positive 30.01. So 30.01. Moment at D is positive 14.07. 14.07. And moment at section 1 is 31.89. So this will be 31.89. So these are the points. Now we know from A to C we have a UDL. So the bending moment diagram will be parabola. So this has to be joined with a parabola. And from point C to D there is no load. So it will be a straight line. And from D to B it has to come down to the negative region, and from B you have to draw it like this. So this is the bending moment diagram, and these are the significant points. Above the reference is positive and below the reference is negative. Okay, if required we can calculate these points of contraflexure by considering moment at that points and differentiating it with respect to x and considering it as 0 to find the distance x. And the next component is elastic curve. So for this we have to draw the fixed beam without the load. So from point A to this point it has to hog. From this point till the other point of flexure it is sagging, so this has to sag, and from this point of contraflexure till the other point it has to hog. So this is our elastic curve. So this completes examples of fixed beams using consistent deformation method. In my subsequent videos I'll try to solve some examples on Clapeyron's 3-moment theorem, so keep following.